Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second in the series on Smith charts and the first of the foundational videos. In this video, I'm going to be covering the whole realm of resistance and conductance, impedance and admittance, reactance and susceptance. Because using Smith charts is all about matching impedances, it is important for us to have a handle on this. Now in the second part of this video, I will spend some time describing two methods of eliminating the reactive portion of an impedance. Now this treatment does not speak to impedance matching. That is reserved for when we get to the Smith chart itself. If you find this video helpful, click on the like and subscribe to the channel. Now, on to the wild world of impedance. The first thing we're going to talk about is resistance versus conductance, impedance versus admittance. Well, depending on what you're going to be doing when you're using the Smith chart, you may choose to operate in the world of conductance and admittance as opposed to resistance and impedance. So we need to be sure that we have a handle on some of this stuff. Now, you're going to be seeing a lot of interesting math here. And just relax, you don't need to have the ability to sit down with a pen and paper and do all the math. You need to understand the concepts. Now, some of you, as the inquisitive experimenters, may be more math oriented. So I'm going to put some of this math in here so that you can experience that. So first of all, resistance versus conductance. Resistance is the name given to that property which describes how a substance opposes the flow of current in a circuit. Conductance is just exactly the opposite. It is the name given to the property that describes how well a particular material conducts electricity. And so you can probably guess that resistance is equal to 1 over conductance, and conductance, represented by the capital G, is 1 over resistance. The units for resistance is ohms. The units for conductance, MHO. Yeah, that is indeed ohms spelled backwards. Now, when we talked about resistors in series, that's the easy one. The total resistance is equal to the sum of the resistors in series. But have you ever wondered why the equation for resistors in parallel looked so funky? 1 over R1 plus 1 over R2 plus 1 over R3 and so on, 1 over Rn. This has always been kind of clunky, and we didn't necessarily understand what was going on, but notice something. See this term here, each of these terms here, conductance, represented by the letter G, is equal to 1 over resistance. Ooh. So we could rewrite this as 1 over G1 plus G2 plus G3 plus ... G sub n. So what we're doing is we're adding up the conductances in the denominator. But now we remember too that resistance is equal to 1 over G. Well, this whole business here is the same as the sum of the G's, or the total G's, the total conductances. And if resistance is 1 divided by conductance, well then resistance total is equal to 1 divided by the total conductances. Oh, well now this equation makes a whole lot more sense. Now, some of the terminology associated with all of this stuff, you're going to notice that as we talk about them, that they kind of were working hard at finding names that are kind of the same, that kind of mean the same thing but have different words. They're equivalents. So we see, for instance, resistance. So you're resisting the flow of current. But we can also impede the flow of current. So you can see DC. This is the DC stuff up here. And this is the AC stuff down here. So we have resistance, we have impedance, we have conductance, and admittance, again, terms that are kind of synonymous. But the big difference is with impedance, it includes more than just resistance. With impedance, which is represented by the capital letter Z or Z, it is a complex quantity because it includes not just the DC stuff, the purely resistive stuff, but it also includes the reactive components like capacitors and inductors. And so you see it has a real component. R is the resistance, which is also the real portion. This is purely resistive. It has no reactive component to it at all. And then it has the reactive component, which is represented by the letter X, which is reactance. And if you've done any amount of electronics at all, you remember that X sub C, which is capacitive reactance, is equal to 1 divided by 2 times pi times the frequency times the capacitance. And inductive reactance, you've been told, is equal to 2 times pi times the frequency times the inductance. This is capacitance in farads. This is inductance in henries. Well, these equations are, well, technically incomplete. They're almost right, but not quite. The reality is capacitive reactance is equal to minus J divided by 2 times pi times the frequency times the capacitance in farads. And inductive reactance is J times 2 times pi times the frequency in hertz times the inductance in henries. And you say, well, what on earth is this J business? Well, J is this inescapable but impossible number of square root of minus 1. Now, if you remember, minus 1 times minus 1 equals plus 1. So if you have anything squared, it's always, the square is always a positive number. So how do you get this? Well, like I said, it's the impossible number. Knowing this, though, the square root of minus 1 equals J, then we also remember that J squared equals minus 1. And that plays into all this fancy schmancy math that you get to do. So impedance includes the part that does not change with regard to frequency, and it includes the reactive component. And you notice in these equations, frequency is part of this equation, and frequency is part of this equation, which means that as frequency changes, the capacitive reactance and inductive reactance are also going to change value. They are frequency-dependent entities. And so with capacitive reactance, as frequency goes up, because frequency is on the bottom, the capacitive reactance goes down. With inductance, as frequency goes up, because it's right here, the frequency goes up, then inductive reactance increases. So, suppose that we had a component, just as an example for all of this, suppose that we had some component. We don't really have an idea of exactly what it is, but we do know that it's composed of this. There's a 34 ohm resistor in there, and there's a 10 microhenry inductor. And here's our component, and we have terminals. Now we want to describe what the impedance is of this. Well, the first thing that we need to do is take this and determine what this reactive component is, X sub L, which remember is J times 2 times pi times the frequency times the inductance, which is 10 microhenries. So right away we say, well, we don't know the inductive reactance because we don't know the frequency. So let's just say for giggles that frequency is going to equal 10 megahertz. So now this becomes J times 2 times pi times the frequency, which is 10 megahertz, or 10 times 10 to the 6th, times 10 microhenries, and microhenries is millionths of a henry, so that's 10 times 10 to the minus 6, and this all comes out to 628.3, so it's J 628.3 is X sub L, and that's in ohms. Okay, so there we go. We know the inductive reactance at frequency of 10 megahertz. So now we can write what the impedance is. Pretty straightforward. We have the impedance is equal to this 34 ohm resistor, and this is plus J 628.3, and there is the impedance of this particular component. Now, like resistance, Z total for series components is equal to the first impedance plus the second impedance plus the third impedance, and so on to the nth impedance. Very simple. Also, like resistance, total impedance for parallel is also 1 over Z1 plus 1 over Z2, and so on. But also like resistance, we can simplify this operation for us if we want to operate in terms of admittance. Now, admittance is the same with impedance as conductance is to resistance. So we have this admittance, which is represented by a capital Y, is equal to 1 over the minus 1 over the impedance. Excuse me, 1 over the impedance. We'll do this again. Admittance is equal to 1 over the impedance. And the units for this is Siemens. Now, because impedance is a complex quantity, R plus Jx, that would also mean that admittance is a complex entity made up of the real part, G, which is the conductance from here, the purely resistive portion, plus J times B, which is the susceptance. Susceptance. I told you that they worked hard at these terms. Susceptance. And the units for susceptance is also Siemens. So with the impedances in parallel, we saw Z is equal to 1 over Z1 plus 1 over Z2 plus 1 over, and so on and so forth. That is the same as 1 over Y1 plus Y2 plus Y3, and so on. So we have impedance versus admittance, and when we may be wanting to operate in this realm, rather than having to do all this ugly math here, we can do all this nice simple addition math, and then in the end, when we're all done, convert it back into the impedance realm. All right, the next thing that we need to be talking about is how to eliminate the reactive part of an impedance. And we'll talk about that next. Next, we're going to be talking about eliminating the reactive portion of an impedance. I want to emphasize that this is not impedance matching. This is just eliminating the reactive portion of the impedance. It is a method that we will be using when we get to use the Smith chart, when we are doing impedance matching. So let's get into exactly how to go about doing that. So one of the things that we want to do with a Smith chart is to be able to create perfect impedance matches. And in order to do this, we most often want to be able to eliminate the reactive part of the impedance of the load. And there are two different ways that we can do this. The first way that we can do this is we can put in a reactive component in series. The second way we can do it is put a reactive component in parallel. So we're going to talk about each of these here. So to begin with, let's talk about reactive component in series. Now, when we're talking about a reactive component in series, you have some impedance, which is equal to R plus JX. Now remember that in series, the total impedance is equal to the sum of the impedances, right? So let's suppose that we have an impedance here of 50 minus J230. That's a really bad load. This looks beautiful, but this is really ugly. And we want to get rid of that. So we have this impedance. Here's our impedance here. 50 minus J230. So what we do is we put another component in series with it, which has the impedance of plus J230. So this becomes Z1, this becomes Z2. So Z total is equal to Z1, which is 50 minus J230. Okay, so this is Z1. Now we're going to add Z2. Now this is a purely reactive component, which means that its real part is 0. So we're adding 0 plus J230. We collect the real parts together. We collect the imaginary parts together. So we have 50 plus 0 plus minus J230 plus J230. So notice that we have a minus J230, we have a plus J230. That goes away. 50 plus 0 is 50. So the total impedance here is just simply 50. Now we have our perfect 50 ohm load that we want. The second way we can do this is to put a reactive component in parallel. So we have, so I'm going to write up here, 2 parallel. So we have our ugly component here that has the impedance of 50 minus J230. And we want to put another component in parallel with it in such a way that we get rid of this. Well, the answer is not plus J230 because it's in parallel. In this case, what we have to do is we have to operate in the realm of admittance. And so what we have to do first is translate this into admittance. So we have admittance Y1 is equal to 1 divided by 50 minus J230. Well, that's kind of ugly math because you never want an imaginary or complex number on the bottom. And you go through all of this math and you end up with the admittance being 0.000903 plus, notice how this sign changed, plus J 0.00415. So here's our admittance value, Y1. We want to get rid of this imaginary part, which is the imaginary part of the admittance of this load. So that means, this being Y2, that means that Y2 has to be equal to 0 minus J 0.00415. When things are in parallel, you add their admittances or conductance. And so Y total is equal to this blob, I don't feel like writing all that, plus this blob, but you notice we have this, plus and minus. So these end up going away. And what you're left with, yt is equal to 0.000903. Notice, no more imaginary part. So there you are. That's how we get rid of the reactive part of a misbehaving load. So there you have it, the whole realm of resistance and conductance, impedance and admittance, reactance and susceptance, as well as how to eliminate the reactive portion of an impedance. In the next video, I will be covering transmission lines, velocity factor, and electrical length, as well as how impedance can change along a transmission line, while at the same time the SWR isn't changing. If you found this video helpful, please click on the like and subscribe to the channel. In the meanwhile, thanks so much for watching. Toodle-oots.